So good evening, everyone. Welcome to the October virtual meeting, the astronomy section, Rochester Academy of Science. Thanks for coming. So we're meeting again virtually. I'm pretty happy to say that we've been able to meet virtually from April through now. We reacted pretty quickly, and we had some help from Dave Pesch and his group Pluto donating this service to us. So that's been a godsend for us to be able to meet this way. So I want to thank Dave for giving us that opportunity. So thanks, David, and your company for donating this service. If we were using something like Zoom, we would probably have to pay for service beyond a certain period of time. I think it's like 40 minutes you get, and then you can only have so many people. But we've had over 100 people on these calls, so glad to. We're very happy that Dave and Pluto have donated the service to us. So thanks so much, Dave. All right, so how this works is if it gets noisy, you can mute yourself. You can leave your microphone on if you want to say something. You can certainly use chat that's on the left-hand side. You can see who's here in the left-hand side. And then next to that, there's a chat at the bottom. You can send a message to a public chat. If you want to chat somebody individually, you can click on their name and chat to them directly. For the talk, what I'll do is you want to chat me the questions, and if it's appropriate to interrupt Scott while he's talking, I'll interrupt him with the question. But we'll have questions at the end of the presentation anyway. It's also best to talk with a headset if you have one on. It's you get less background noise and that kind of stuff. So for future reference, if you have a headset, wear it. It makes it a lot easier to do this. That's what I'm using as well. All right, with that, let's get started. So welcome, everyone. My name is Mark Minerich. I'm your president of the astronomy section. I'm glad to be able to host you this evening. We'll have some announcements, and then our featured talk tonight is by Scott Kenyon, who's up there on your screen. He's an astrophysicist at the Smithsonian Astrophysical Observatory with a talk entitled "Pluto Strikes Back." Look forward to that at the end of this here. All right. So any observing recently that anybody wants to contribute to? I put up a picture of Mars that Kevin Lyons took on the 28th, I think, with incredible detail through a 10-inch Meade at f20. Looks like he put a Barlow lens on his scope and was able to get a really nice image of Mars. But has anybody looked at some of the planets over the last few weeks? Yeah, just an incredible image. Yeah. Well, if you haven't, I'll go ahead.
Yes, Mark. Yeah, of course, Jupiter, Saturn, and Mars.
Yes. Yeah, you were telling me you had to scope out with some neighbors looking at the planets. Yep. Anyone else had a observing experience I want to share? Yeah, so Kevin has inspired me with this image of Mars that I want to try to get an image of Mars like that, perhaps even better because we've got a bigger scope up at the Ferris Center. We've got a 14-inch, and we could get to if we put a Barlow on it, we could probably get to f22. So now I feel challenged to try to look at at Mars. So Jeff said, "How about the wildfire sunsets?" That reminds me that. I actually did try to go to, if you were on earlier, I tried to go down to Cherry Springs and go to the unofficial Black Forest Star Party because there was no star party, but there were people down there. There were at least 100 campers down there, or campsites down there, and telescopes out in the field. But the wildfire smoke was so bad that you could not see anything for the bottom 30 degrees of the sky. So 30 degrees up was before there was nothing. And then you started to see some stars, and straight up even you could not really see much. You could see the summer triangle up there, but really not much in the middle of it. You could maybe make out Cygnus. It was really bad. It was terrible. Sadly, I just wish I just wish we didn't have all the fires out there. At least the smoke would go away. So pretty sad. Any other observing chronicles? All right, we'll move on. All right, so we've been having some virtual star parties. We've had 3 sessions so far, and they're announced on our in our email list. In this month's newsletter, there are links to the prior star parties, and there's a couple links for each star party. One link is for the meeting itself. It's just like this, and we talk about what we're going to show, and then I show recorded clips of what we observe as part of the video. So pay attention to those. If you're not on the astronomy section email list, let me know. You can actually put it in the chat. Let me know that you're not and you want to get on, and I'll talk to our admin to get you into the email list. Which reminds us that we are going to have another virtual star party on Sunday. The Celestron, the C14 is now back in F11 mode. We were in the Hyperstar F1.9 mode, which made us a wide field. Now we're down to its native F11 mode. It's been collimated, and we'll have a planetary session on Sunday at 7:30. So same meeting time as tonight. We'll take a look at Jupiter, Saturn, Mars. We'll try to look at Uranus and Neptune as well. So if you're interested, come at this same time on Sunday, right to the same site, same link, everything. I sent that out yesterday, and I'll send another link out on Sunday just to remind you for the virtual star party on Sunday night. It won't be long, probably 45 minutes, maybe up to an hour at the most for the whole thing. So it won't take up all your night, but it could be a fun beginning to your evening. Any questions on the star party? Okay. All right, so here's the upcoming events. We'll have a board of directors meeting that's virtual. That will be on Wednesday at 7 o'clock. If you are a member and you want to attend, shoot me a note, and I'll be glad to send you a link to the meeting. ASRAS members are welcome to attend, so anytime you want to join us for the board of directors meeting, we plan our monthly schedule, the activities that we do. We're going to schedule our election actually next month. Be glad to have you, and then anything else that we can do in the meantime. So just let me know if you want to attend. I'm glad to send you a link. Also coming up is an open house on Saturday the 17th at the Ferris Center from 12 to 4. And actually that same night, we're actually going to be doing member observing. And the whole time we're there, we're observing COVID protocols that we'll do later on. And we'll do it for this event and later on. And these are the protocols, and they'll be posted all over the site when we're there. This is the 3rd or 4th time we've been doing this. So if you've been, you'd kind of know the routine. But if you haven't, we want to make sure that if you're going to go, sign in when you arrive. If we need to do contact tracing, we'll have your name so that we know if in the event that something happens, who was there and who was in contact with an active case of the coronavirus. But we'll have wipes and hand sanitizer right there when you sign in. We want to ensure that everybody's 6 feet apart. If you're not 6 feet apart, certainly you need to be wearing acceptable face coverings. The building needs to be at under 50% of capacity, which is now means we have a maximum of 30 people in the building. Typically, we can get 60 people in that building, but half of that would be 30. If you're in the 2 bigger observatories, the cave or roll-off buildings, no more than 4 people in each of those. Both bathrooms will be clean the day of the event, and they're able to be used. If you make sure that if you go into the bathroom, wipe the faucet handles with the disinfecting wipes that are there before and after you use the restroom. Wipe the toilet seat if you use it, or handle it before and after use, and then throw everything in the trash can. Don't flush them. We're on a septic system, so it's easier to get rid of it if you toss it out in the trash. Then wash your hands. If you're observing, use red lights only after dark. That way we don't blind anybody who's got their night vision all squared away. And then have a good time. So, and we've done this a few times now. It seems to have worked pretty well. So I would welcome you to come on Saturday the 17th for observing at dusk, or if you want to come for an open house and look at get a tour of the facilities, how to use the scopes, all that kind of stuff during the day. So look forward to that on the 17th in a couple of weeks, 2 weeks from tomorrow. In November, we're going to do a virtual election. So we'll actually take a poll for the election for our board of directors right here. This is our slate for 2021. I wrote 20. It's a 2020 is the election, but this is our 2021 candidates. So I'll be running again for president. Dave Bishop for vice president. Ted Lechman is going to take over for Mary Winzenberg as secretary. Mary's had a number of things come up at work, and she'd like to step back for a while. And Ted would like to come back into the board of directors, and so he was a director last year, and so he's said that he will take over as the secretary for 2021. Bob Easterly is up for our treasurer, who's been as steadfast as our treasurer over quite a number of years. And then our directors are not changing. The directors are Mark Dudley, Tony Golombek, and Bill Rogers for 2021. So not a whole lot of changes other than shifting our secretary for next year. And I want to thank everybody there for the job that they've done over the past year and stepping up again for next year. So thank you very much. This will vote on next month. Excuse me. All right. I don't have a speaker name yet for next month. I know Dave is working steadfastly on getting us a speaker for November. We've got, I think we have an emergency plan, don't we, David? Dave's going to unmute himself now.
Did you guess? Yes.
Yes.
No, I do got an emergency plan. We'll figure something out, though.
All right. We'll stay in touch. We will not leave you hanging. We just don't know ahead of time who that'll be yet. So
it has to be one of us. It has to be one of us.
That's right. All right. And also November, the open house is on the 14th. It's also the same day as member observing. So that happens to be a new moon weekend. So the same day that we'll have an open house, we'll also have member observing in the evening with the same protocols I outlined for October. And I'll take you all the way to December because we do know who our December speaker is Kelly Douglas, who is a visiting professor of physics and astronomy at the U of R. In fact, there's a number of you who are actually auditing her class this semester, the solar system class. And she'll be teaching, she'll also be instructing maybe a couple of classes next semester that we may be able to audit as well. Her specialty is studying large-scale environmental influence on galactic evolution. So I don't have a title talk from her yet, but I just want to get an idea of what she's interested in, and we'll see where that talk goes for December. And that is in place of, unfortunately, that's in place of one of our favorite events, and that's the holiday extravaganza that we usually have at the Strassenberg Planetarium. So because the planetarium is limited to the amount of people they can keep in the building and the amount of people they could keep in the planetarium theater, and that is right now a maximum of 35 people in the theater. That just isn't going to cut it for us. Plus, we usually have food, beverage, and a lot of socializing that goes on in the lobby. In today's environment, it just can't happen, unfortunately. So sadly, we will not have our holiday extravaganza at the Strassenberg this year, but we will have a regular meeting, and Kelly Douglas will be our speaker there. All right, with that, I'm finished. Any questions for me? All right, so I will turn this over to Scott J. Kenyon of the Smithsonian Astrophysical Observatory. And Scott, I will make you the presenter. And all you need to do now is go back in and select your presentation as the one you want to put up.
Where do I do that?
So hit the plus button.
Yep.
And then upload presentation, and it should already be there. You just click the little check mark, the little white ball there. There it is.
All right.
All right, it's all yours. Kenny, can you turn off your video, please?
Okay, well, thank you very much for inviting me to give this virtual talk. I will have two videos in the middle of it where I will share my screen and bring the video up. If there's a problem with that, I can just describe what the videos show if there's a problem with the bandwidth. So let me know if the videos don't transmit very well.
I'll do that.
So I'm a planetary, exoplanetary star formation scientist. And you probably all know that over a decade ago, there was a big controversy over whether or not Pluto was a planet. And there was a lot of consternation over that. And this talk today is really not about whether or not Pluto is a planet, but how wonderful Pluto is as just a planetary object. And so this is Pluto's redemption as an interesting object in our solar system. So the story with Pluto begins in 1915 when, because of irregularities in the motion of Neptune, Percival Lowell used Newton's laws to predict that there would be a planet outside the orbit of Neptune. And so he predicted that in 1915, and they looked and they looked. And you might recall that when Neptune was predicted, it took only a couple years to find it and confirm it and track it. And finally, in 1930, they discovered Pluto. And it was not quite what they expected. It was a lot fainter. It was sort of in the right place. And it had, after some observations, a very strange orbit. Hopefully that will come up. I don't know if you see the slide.
Yeah. Yes,
I'm getting an error called media could not reach the server.
We can see the slide. There's
so you
no
see
motion.
The slide?
We can see it. Yes.
Okay, so I can't see it. So let me figure out what I need to do here. Just a second. There it is. Okay, now I can see it. So Pluto had a very strange orbit, has a very strange orbit to the solar system. So this is a little diagram of the orbits of the major planets, the sun at the center, and then the terrestrial planets, the asteroid belt, Jupiter, Saturn, Uranus, and Neptune, and they're all pretty much in a plane, a pretty flat plane by astronomical standards. And Pluto has a very elliptical orbit, not very circular compared to the others, and very inclined relative to the plane that the rest of the planets have. Inclined about 25 or 30 degrees or so. And sometimes it's actually inside the orbit of Neptune, and most of the time it's outside. And it's in what we call a resonance, where it has two orbits of the sun for every 3 of Neptune, and actually keeps Pluto stable. And so people kept observing Pluto as they could. It's not very bright. It's 12th magnitude visually. And they took spectra and they figured out it's mostly ice in the optical, and they went on. So now we'll get this. In 1978, Christie was taking photographic plates with the Lowell refractor out in Arizona. And one night he saw a little bulge on Pluto on one side. And a few nights later, he saw another bulge on the other side. And he kept taking photographs. This was with plates, so this was really pitifully hard at the time for any of you who have developed photographic plates. So he saw the bulge on one side of Pluto, a few days later on the other side, and then a few days later back on the first side. And he realized that there was actually a moon of Pluto, a period of around 6.5 days. This is not an image from one of his photographs. This is actually an image constructed from Space Telescope data, and not even images. So it turned out that, fortunately, during a time when information you could actually observe Pluto, that Pluto and Charon had a series of mutual eclipses. And when one planet eclipses another, or when one star eclipses another, if you can get nice time-resolved photometry, or measure the brightness of these objects as a function of time, as, say, Charon, the one on the right there, goes across Pluto, it sort of slices it up, and you can see what disappears and what goes away. And then as Charon reveals the rest of the planet, you can see what appears. And so you can make an image of the two planets from these mutual eclipses, and this was what they got. You can see that there are bright spots and dark spots, and that's pretty much it. And that was, the state of the art of what you could do with HST until 2015 or so. So that was in 1978, and Pluto now was more interesting because it had a moon, and it turns out that Charon is about a tenth the mass of Pluto, and it orbits in such a way that the center of mass of the binary is outside Pluto's surface. So it's actually a real binary, unlike the Earth-Moon system, where the center of mass, the point where the two objects orbit around, is actually inside the Earth. And that's because the moon is not a tenth the mass of the Earth. And it sort of lay there for a while until 1992, when Liu and Dave Jewett discovered the first object in the Kuiper belt. The Kuiper belt was proposed by, amazingly enough, a man named Kuiper in 1951, where he supposed that, well, there was no reason for the solar system to end at Neptune, and that Pluto shouldn't be the only object out beyond Neptune. Suppose that there would be objects beyond Neptune. And I don't know if you can see it on this image, but this is the set of images separated by a few hours of the first Kuiper belt object. What Jane and Dave did, this was in the days of they finally had CCD, so they could take very high quality imaging with the University of Hawaii telescope. And they would take an image, and a couple hours later, they would go back and take another image, and the difference between the two images would show an object that moved, if they were lucky, and it would move a few arc seconds, an hour. So, images over the course of the night enough to detect the motion of an object beyond Neptune relative to back on stars, and the motion would be a lot slower than an asteroid, which is a lot closer. So they detected the first Kuiper belt object in 1992, and then there was a whole slew of them detected. There are now 3,500 of them or so with good orbits. And what you have to do is get enough observations when you first discover it so that a year later you can get it again and get an orbit over 2 or 3 oppositions. So after 5 to 10 years, we had this nice little group of rather large objects in the Kuiper belt. You can see Pluto with Charon. And at the time, Eris, another object outside the orbit of Neptune, was a little bigger than Pluto. Then there's Makemake, Haumea, which is another binary, Sedna, which has a very eccentric orbit well beyond the orbit of Neptune, Orcus, Quaoar, Varuna, and countless others, now, as I said, up to 3,500. And that caused a problem among some astronomers anyway, because you had now a lot of objects, in the same part of the solar system, belt, but farther out. These are icy objects, not rocks like the asteroids. And Pluto had been called a planet, and now Eris is bigger than Pluto. So do you make Eris a planet? And do you make Makemake a planet? Do you make Haumea a planet? And a lot of people thought, well, why not? We can call any of these planets that we want to. But a lot of people didn't like that idea. And I don't want to get into all the details of the argument, but my feeling was that some astronomers simply don't want to count past 9. And so they decided that Pluto would not be a planet. And that caused a lot of uproar. And I think this is an image with all the planets looking. Oh no, this is where the objects are in the solar system. Sorry about that. The sun is at the center. The white circle is the orbit of Jupiter. This is a view from the top down. So white circle is Jupiter, the pink circle is Saturn, and then Uranus, and then Neptune in purple. Pluto is the one in cyan that intersects Neptune's orbit. The dots are the bunch of Kuiper belt objects that had been discovered by around 2005 or so. And some of them had circular orbits or nearly circular orbits. Some of them had elliptical orbits like Pluto. And some of them had very elliptical orbits like this magenta ellipse. And so, aside from the fact that there were some that were as big as Pluto, some of them had weird orbits. And so there was a move to demote Pluto from the realm of the planets and call it a dwarf planet. The motivation for that was that the sun is a dwarf star and is not a supergiant star. This is a view of the orbits from the side. So we're looking in the plane of the solar system. The concentric magenta circles, it's sort of a mess in the middle, are the orbits of the giant planets. Pluto is the cyan ellipse, and then the dots are the positions of all the Kuiper belt objects. So you can see that some of them are in the plane, some of them are out of the plane, like Pluto. And so there was this whole group, essentially another asteroid belt beyond the orbit of Neptune. And so there was a big discussion, and in the end, as I said, we called Pluto a dwarf planet with the idea that there would be a bunch of dwarf planets. There would be the main planets, which clear out their orbits, and then there would be the dwarf planets. And this was a nice graphic I got off the web, where you can see the main planets, all 8 of the inner planets, shunning Pluto. And there was a lot of controversy over this. There were, not riots, but there was a lot of upset that Pluto was now not a planet. I mean, it changed the way people, placemats for kids now had to be redrawn, and grade school teachers had to rethink how they would have their syllabus. And so this is a picture of a movie theater that said, "I want Pluto to be a planet again." And the next one is a bunch of people protesting Pluto's demotion with "What would Walt do?" and various other things. All we are saying is give Pluto a chance. And so my interest in Pluto is not so much whether or not it's a planet, but what it can tell us about how planets form, which is one of my main interests, and not only how planets form, planets in the solar system form, but how planets in other planetary systems form. And so the rest of this talk is about how interesting Pluto is, and that's why I call it a story of redemption, because rather than just the argument over whether or not Pluto is a planet, we can marvel what Pluto teaches us about planets that we don't learn from any other of the planets in the solar system, and how we can apply this knowledge to other planetary systems. So Pluto's redemption started with Hubble Space Telescope. Not only did HST use the mutual eclipses to try to get what Pluto's surface and Charon's surface looked like, in 2005 and 2006, HST discovered 2 moons orbiting the Pluto-Charon system. And they don't orbit Pluto or Charon, they orbit Pluto and Charon. So they're a circumbinary set of satellites. The inner one is called Nix. The outer one is called Hydra. These are actual images. You can see that they're very faint compared to Pluto. As I said, Pluto is about 12th magnitude optically. Nix and Hydra are around 24, 25. So you really did need HST to detect these things. And they made these images because New Horizons was the New Horizons mission was going to Pluto, and they wanted to make sure that it wasn't going to hit anything while it traversed the Pluto system. And so they did very deep imaging, and they first discovered Nix and Hydra. And later, they discovered 2 more satellites. On this image, this is about the best image that I've been able to find of the 4 satellites showing their orbits. You can see Pluto and Charon, and then you see the orbits of the 4 satellites as little ellipses. Nix and Hydra are labeled. The other 2 are labeled P5 and P4, and this is before they got names. P5 is Styx, and P4 is Kerberos. I'd have thought that it would be Cerberus, but there is an asteroid called Cerberus. And so since Pluto, the satellites of Pluto and Charon have to be named after something in the underworld, they decided to go with the Greek name of Kerberos. You can see that Nix and Hydra are somewhat brighter than Styx and Kerberos. So they could be bigger. They could simply reflect light better. And it would take the New Horizons mission to tell us which of those was correct. But now we have 4 satellites orbiting this binary planet. And that's unique in the solar system. And for those of us who study planets, that's pretty cool because we get to learn how circumbinary satellite systems work. Every other satellite system in the solar system is a bunch of satellites orbiting a single planet. So that, we have the 4 satellites. I'll wait for my slide to come up so I can describe it. And what I'd like to go through now is what does Pluto tell us about how not only Pluto-Charon formed, but how did planetary systems form? And this is a graphic of the protosolar nebula, the protoplanetary disk, or the earliest days of the solar system, when the sun was just a young tyke, only a few 100,000 or maybe 1 million years old. It's the yellow dot at the center. It's surrounded by a swirling disk of hydrogen, helium, and dust particles. It's also ejecting mass in a bipolar outflow, which is an artist's conception here. And the way we think planets form is that dust particles in this disk agglomerate. They agglomerate a lot like the dust bunnies under your bed. Since we live in the Northeast, we often have wood floors. And after a couple of weeks, stuff can accumulate on the floors, and it sort of agglomerates together and makes little collections of various jetsam and flotsam in your house. And usually you get rid of it after a couple of weeks or so. But you could imagine how big a dust bunny might get after 1 million or 2 million years, because in the solar system and in this disk, it's just this accumulation process just continues and continues and continues. So the dust in this disk is originally roughly 1 micron particles. They agglomerate together and agglomerate and become millimeter to centimeter sized particles. Those agglomerate together in several ways that we don't quite understand yet to become kilometer-sized objects or maybe larger. And those kilometer-sized objects have self-gravity, and so they collide and merge and eventually grow into a planetary system. And that's what happened with Pluto-Charon. They agglomerated, and Pluto was somewhat outside the orbit of Neptune, and so was Charon. And there are several theories of how they became a binary planet. You might think, well, they just got close enough together and captured one another. It's hard to make that work in nature in a way that is follows the laws of physics. And so the simplest model now is that Proto-Charon, which is shown in the upper right here, collides with Proto-Pluto. And it's a glancing collision. It's not a head-on collision, but Charon sort of skims the surface of Pluto, and that skimming slows it down just enough to be captured. Aside from being captured, it is then in orbit around Pluto, and the debris that's kicked up in that collision makes a satellite system. And now I'm going to try to show my video. So the idea after this is, this is a schematic. This isn't exactly what it looks like, but Pluto and Charon are there in the center. And the debris is sort of in a ring. Let's see if I can share my screen. All that. Well, I'm going to try sharing the screen. Can you see my screen?
I still see the evolution after impact graphic.
Okay, so it's not.
So Scott, maybe I can suggest you shut off your video feed, and I think it's frozen, and then maybe that might free up some bandwidth for you.
Okay, sure. Okay, well, that doesn't seem to work. So I won't waste your time with this. So the idea is that after the impact, you have some kind of ring of stuff around Pluto and Charon. And the satellites are, at this point, lots of small particles, centimeter to millimeter, maybe up to meter-sized objects. And as this system evolves, the particles are originally on very elliptical orbits. This ring is shown as a nice circle, but the orbits actually go close to Pluto and Charon and then come back out. So they're fairly elliptical. And as they circularize through collisions, it pushes this ring outward. And as it pushes the ring outward, it makes the things collide and they agglomerate, and eventually you have a set of satellites. And those are the kinds of calculations we do. I seem to have lost my presentation.
Try to upload it again, or try to pull it from the upload area again. You're sharing.
Okay. Sure.
Or stop sharing the screen. Yeah. Okay, just hit confirm, and you should be good.
Okay.
There you go.
Okay, so let me see if I can share the screen and show the video. No, all right, that's fine. So I'll just go on. So the end result of this calculation is something that looks like this. When we do numerical, what we do is we actually do numerical simulations on a supercomputer to simulate what happens to all these debris particles that are orbiting Pluto and Charon. And after about 1 million years, it looks like this. And this was a simulation where we actually made 4 satellites in approximate orbits to the 4 known satellites. So we made a big thing, Hydra, another big thing, Nix, a smaller thing, Kerberos, and a smaller thing, Styx. And we can't make anything in this. We can't make anything in this black region here because all of the orbits are unstable. And so Styx, near the inner part of the disk, this disk, is actually the innermost satellite you can have in nature, which is pretty amazing. We also predicted that there would be 3 other satellites, which are shown in green here, which are outside the orbit of Hydra. And at 1 million to 10 million years, there is a lot of debris left over. And over the next 10 to 100 million years, that would go away. The satellites will clear out their orbits. You can see that they're starting to do that. So Hydra, which is the most massive, has already cleared out. You can see there's a lot of, black region here. And that's where there's no stuff. So it's cleared out a large fraction of its orbit, and the other satellites are starting to do that as well. So we made this prediction that there would be 3 smaller satellites. We predicted that Styx and Nix would have radii of around 20-ish kilometers or so, maybe up to 30, and that Kerberos and Styx would be a lot smaller, more like 5 to 10 kilometers rather than of order 20 kilometers. And these little bitty satellites out here, which hopefully you can tell are smaller, would be on the order of 1 kilometer or maybe 3 kilometers, something like that. So that's one of the great things about astronomy and any physical science or even biological sciences is you have an observation, in this case 4 satellites orbiting Pluto Charon. You come up with a theoretical picture for how they came to be, and you try different parameters, and we actually did probably 20 or 30 different calculations before we got one that we liked. Some make too many satellites, some make too few satellites. And not only do we get something that looks sort of like the Pluto-Charon system, but we predict that there would be extra satellites. And that's something that you can go out and test to try to test the model. So, something like 20 years ago, Alan Stern and a bunch of his collaborators developed the New Horizons spacecraft, which was sent to Pluto, wandered past Jupiter, it got a little bit of a gravity assist as it passed Jupiter, and it went out to Pluto. And this is an artist's conception of New Horizons and Pluto and Charon. The sun is in the back. Charon is in between Pluto, which is in the foreground, and the sun. And so New Horizons had lots of different instruments. The ones that we were interested in were the 2 imaging instruments, which had a big enough field of view to look for new satellites. So New Horizons went out, and it took about, it flew through the system in less than a day, and it had amazing images. This is an image of one of the first images of Pluto. And lots of us who had worked on Pluto were asked by the New York Times beforehand and other publications what we would see. And pretty much everyone said craters, lots of craters. Well, it's hard to see craters here. So that was not a good prediction. You see, the terrain doesn't look so different from the moon in a certain way. You see, things that look smooth. You see things that look a little bit cratered. There are dark regions, bright regions, just like on the moon. And that was really, one of the first spectacular images, and that was a wonderful surprise. The most surprising thing was that there was flowing ice on Pluto. Everyone knew there was nitrogen ice and water ice and ammonia and methane ice, but no one expected it to flow like a glacier. And this, you can see, the nitrogen mountains. They're frozen nitrogen along with some other frozen things. And then you see sort of flat plains. And so this was just an incredible view that you really didn't expect a lot of terrain on Pluto. And in the end, the mountains, the height of the mountains on Pluto relative to the size of Pluto. So if you take the height of the mountains above the surface relative to the radius of Pluto, those are larger than Mount Everest, or even something like Mauna Kea from the seafloor to the surface or the peak of Mauna Kea. So they're pretty amazing mountains, and they're all of frozen stuff. They're not really rock. The claim is, I'm not a geologist, but the claim is that stuff actually moves around. So this is an image of Charon. You can see some craters. You also see some dark spots. And there is on the sort of at 2 o'clock to 3 o'clock, you can see sort of a dark gash in Charon. That's a big canyon, which is relative to Charon's size, deeper than the Grand Canyon or deeper than Waimea Canyon on Hawaii. And so both Pluto and Charon are nearly completely round. Here are some images of Nix and Hydra. They didn't have a lot of time in going through the system. And so the images of the satellites that they got were about as good as they could do, because they didn't, they had no way of changing the trajectory of the satellite as it went through the system. So wherever the moons were is what they got. You can see that Hydra has some craters on it. Nix has, it looks featureless here. I think we have Kerberos, which looks sort of like an ice cream cone in a certain way. It has it looks like, actually to me, two sort of snowballs stuck together. It has a thin rim where they join. There wasn't a good image of Styx. You can see this here in the family portrait of the system. You can see that Nix and Hydra are much bigger than Styx and Kerberos. The amazing thing about the 4 satellites is how reflected they are. Pluto and Charon each reflect about 30% of the light that they receive, which is pretty reflective. Styx, Nix, and Hydra, Hydra's the best. Hydra reflects about 70% of the light that it receives. Nix a little less, Kerberos a little less, and Styx a little less. But they're highly reflective. And it's as if they had very nice water ice surfaces. And so you can see they're not very big. Kerberos and Styx have radii of around 5 to 10 kilometers. And Nix and Hydra are somewhat bigger. And these images are not to scale. The perspective, it looks like Nix is a lot bigger. And it is somewhat bigger, but not quite as big as it looks like. New Horizons didn't stop there. Later, it went on to see another Kuiper belt object, which they named Ultima Thule, and they've now renamed to Arakoth, and I should have changed that. It's now called Arakoth. But this is another object that looks like two roundish objects stuck together. It turns out that they're flattened. This is a top view, and they're more like 2 very thick pancakes stuck together. But again, you can see in the upper part of the right lobe of Arakoth, you can see see some craters. And in both Arakoth and Charon, the craters are numerous enough that you can get the number of craters as a function of their sizes. And these objects are supposed to be bombarded by objects in the Kuiper belt. So you can learn about the size distribution of small objects in the Kuiper belt by studying the craters on these objects. So the sad thing about the New Horizons mission is that there weren't any new satellites. They looked pretty extensively. They did lose some opportunities to detect satellites, new satellites, with a computer failure. So they lost about a third of the images that they might have gotten. But in any event, then they didn't see any satellites bigger than 2 kilometers in a region that's roughly twice the orbit of Hydra. So that was a disappointment to them and to us. Our prediction said 1 to 3 kilometers, so we're still safe. But it was disappointing that there's nothing bigger than 2 kilometers. And the one thing they could not do is look at the satellite masses. They can't really measure the masses of the satellite. You can measure the masses of Pluto and Charon very well because you have their orbits. You measure their, you measure their orbits very well, and you can get their masses. But the satellites, their gravity isn't enough to perturb anything, so you can't really get their masses. So that was one of the next steps in our study. And what we tried to do is, I'm not sure I'll be able to show the video, but this is what we tried to do is figure out where satellites could be in the system. And so we did a bunch of simulations, and we figured out, based on various other numerical simulations, that the 4 satellites are as massive as they can be. That is to say that if they were any more massive, their mutual gravitational perturbations of one on the other would eject them from the system. So, okay, well, let's see if I can share the screen for this. Can you see this video?
Try to play it now, Scott.
Okay, I'll give it a try. So this is a time lapse of what happens when you put small particles, say bees, in around Pluto, Charon satellites. Function of time, the time is over. I can play it a couple times to give you an idea. And if this works, I could also try the other video if you'd like. And anyway, after 10 million years or so, you can see that there's really nothing left. And if we ran this for another, say 100 million years, the band just inside the orbit of Styx would disappear, and the band outside Hydra would thin out. But outside the orbit of Hydra is really safe for satellites. And so what we predict again that there could be satellites outside the orbit of Hydra. And the amazing thing about that is that if JWST is launched, I'll play this video again, you can just see it goes away. And what's happening during this evolution is these particles get too close to any of the 4 satellites, and their orbits are perturbed. And they're more and more and more too close to Pluto or too close to Charon. These particles in the solar eject the solar system, but they are ejected Pluto Charon, and so Pluto Charon returns a bunch of stuff to the solar system over time from this giant impact. Okay, so I will close this. Stop sharing the screen. Okay. So the nice thing about this experiment, it's a numerical experiment, not a ground-based experiment, is that if there are kilometer-sized or even half a kilometer-sized satellites beyond the orbit of Hydra in this black region out here somewhere, imaging with the James Webb Space Telescope can detect them. So if you take a lot of pictures of Pluto Charon with this instrument, and you have to use infrared imaging, you can detect small satellites. And the next generation of space telescopes, which are in the planning stages, and who knows when they'll be, whether they'll be approved, and if approved, when they'll launch, those could get down to 1/10 of a kilometer or perhaps even smaller. And so we can, with these other instruments, we'll be able to learn more about the Pluto-Charon system. And so, we're not going to send another satellite there to visit anytime soon, but using space telescopes that we have, we can try to detect more satellites. Styx here and Kerberos here are at the limit of what Hubble Space Telescope can do. It's really hard for HST to get any fainter satellites than what it's done. It's a challenging observation on its own, and getting any fainter is just too hard. So I hope this is an image of Pluto being happy. And I hope I've given you some entertainment and shown you what a rich system Pluto and Charon and its associated satellites are. And whether you want it to be a planet or a dwarf planet, it has a lot to tell us about planetary systems, because it turns out that a lot of exoplanetary systems are also, as we call it, closely packed, the way Pluto and Charon's circumbinary satellites are. So, as I said, the 4 little moons orbiting Pluto and Charon are as massive as they can be and be in the orbits. If they were any bigger, any more massive, they wouldn't be there, because their gravity would have ejected them. And we see not only circumbinary planets, but just exoplanets around a single star that are in the same configuration, that are as massive as they can be for the orbits that they have. And it's sort of weird if you want to think about it. And the solar system planets are sort of like that too. You start out with this disk of stuff, and the planets agglomerate, and they agglomerate in a way that makes them just big enough to exist. And if they were any bigger, because they could accrete more, but they don't for some reason. And so what we're trying to do, in these next stages of understanding how planets form, is to try to understand, well, why did they get as big as they can without, disrupting the whole system? And maybe there are a lot of systems that do get disrupted, but there are a lot of systems that get as big as they can and stay stable. And there aren't as many systems as you might imagine that never get that big. So we're really trying to understand the way planets form and how they manage to have the masses that they have. And why does the Earth have the mass it has, and why isn't it 50% less or 2 times larger? So I'll leave it there. I'm happy to entertain questions, and I hope that you have a greater appreciation for Pluto and its surrounding moons. Thank you.
Scott, thank you so much. Virtual applause. Virtual applause. I have a number of questions that are queued up here for you. First,
I will leave my video off.
Okay, fair enough. From Zwolonki, he says, why do Nix and Kerberos have different reflective percentages, yet they are made from the same material?
Well, that's a good question. The short answer is we don't really know. That the idea of the stuff that these 4 moons are made of is that it's ice from either Pluto or Charon. There are competing pictures of where the icy debris actually comes from, but it gets spewed out. And so it's not clear if they should all start out with the same reflectivity or albedo, as we often say. because you could imagine that since Pluto and Charon aren't, from the images from New Horizons, you can see that Pluto and Charon don't have the same reflectivity across their surfaces. Perhaps one satellite got a little more of the dark stuff on Charon or Pluto than the other satellites. The other thing that can happen is that while these satellites have been orbiting Pluto and Charon for 4.5 billion years, they get bombarded with little particles. And you could see some crater-like things on the satellites. And it could be that the stuff that bombards them is dark, or it reveals some dark stuff below the surface. And so since they have different histories of getting bombarded, that could also produce different reflectivity.
Thank you. Another question from Don. What is the attraction in an Earth dust mote? He was talking about your dust bunnies. Is it electrostatic or gravity? And how large does a mote in space have to be to have gravity?
I'll answer the last part first because that's easy. Large objects with a radius of around 1 kilometer to 2 kilometers, it sort of depends on whether they're composed of ice, like water ice, which would have a density of 1 gram per cc, or rock, which would have a density of something like 5 or 6 or something. But anyway, a few kilometers objects have enough self-gravity that they will deflect the trajectories of small particles that go around them. And so they can attract particles. And something that's 100 meters doesn't quite have enough gravity to attract things. The smallest dust grains, which are about 1 micron in size, what they do is they actually do collide. Some people think that, it's sort of a Brownian motion kind of thing. So they're all sort of they're orbiting the star, but they have small relative motions. So they will collide. And if they collide at the right velocity, some people think electrostatic forces are important. Some people don't. But everyone agrees that they, especially if they're icy particles, they'll collide and they will merge if they collide at low enough velocities. If they collide at high velocities, they may disrupt one another.
David asks, how big are Nix and Hydra?
Nix and Hydra are about 20 kilometer radius, give or take.
Tony asks, which N-body models were used for the Pluto Charon system simulation results shown? And what kind of numerical integration method does it use?
Okay, so we have our own N-body model, which we've tested against other models, other N-body calculations. One of the most famous ones these days is called Rebound, which is open source. And we've tested our code against that and others. Ours is our own, we made it ourselves because we started doing this 20 years ago when publicly available things weren't available. And it uses what's called a symplectic integrator for some calculations, and then it has a higher order integrator for other applications. So the type of integrator we use depends on the calculation we're doing. So when the simulation that I showed you where the particles were going away as a function of time, that's a symplectic integrator. And what that does is it has a what we call a Hamiltonian that conserves energy very well, but doesn't worry too much about the phases of things. And so it's very good for tracking whether or not something is stable in its orbit, but it's horrible at figuring out if two objects collide with one another. So we have higher order integrators that allow us to resolve the collisions of individual objects. So when we do a calculation where we're forming planets, we use these higher order integrators because we want to know if this 10-kilometer object collides with this 2-kilometer object.
That's pretty cool stuff. Jeff, did that answer your question? If you could type that in. Nick asks, are the satellites all in the same plane?
Amazingly enough, they are I didn't mention that too much, but the amazing thing about the whole system is that Pluto and Charon are in a circular orbit with one another, and it's tidally locked. So they keep the same face, the same hemisphere always views, if you're on the hemisphere of Charon that faces Pluto, you always see that. So there's no real orbiting of Pluto and Charon around each other in the way, say, the moon goes around the Earth. And the four little satellites all orbit, as far as we can tell, also in circular orbits or nearly circular orbits. The eccentricity might be 0.001 or 0.002 or 0.003 or something like that. Maybe even 0.01 in some cases, because it's not clear they can always get to better than 0.01. And they're within a degree or two of the orbital plane of Charon. So it's an amazingly flat system.
Is it tilted? So obviously it's tilted because we see it. We could. Right,
the orbital plane of Pluto and Charon is tilted relative to the Earth, but it also, as we orbit and it orbits, the orbital plane moves around.
That's right.
On the sky. And so for a period of time, the orbital plane, our line of sight was in the orbital plane. So we could see these mutual eclipses of Pluto and Charon. At this point, they're not, the line of sight is tilted, the system is tilted relative to our line of sight.
Okay. Jeff asks, what were the top 5 parameters for your moon formation simulations?
So that what we worry about is, so Pluto and Charon collides with Pluto and it kicks up some stuff. There's the mass of the stuff. And the more mass you have, in a sense, the more you can lose, because you always lose some mass. So the accretion of the satellites is not 100% efficient. So you start out with, you try different masses. And since at the start, we didn't know what the masses were, we had to figure that out. So we start out with a range of masses of the stuff. You worry about what the orbits of the stuff is, and so the orbits are, where is the stuff? How far away is it from Pluto and Charon? And what is the eccentricity of the orbit? And to a lesser extent, the inclination. The inclination of the orbit relative to the orbital plane of Pluto and Charon is not so important because collisions flatten that out really quickly. So the eccentricity of the stuff is important, the total mass of stuff, and the orbit. So those are the 3 things. And then you worry a little bit about what the masses of the particles are. How big are they? And because if you eject a lot of stuff and the amount of stuff you eject is like 10 to the 22-ish grams. And that's about a thousandth, say, the mass of Pluto. And if that's all in 1 kilometer objects and they never collide, they don't stay around very long. They just go away. So you need a size distribution of stuff such that whatever the biggest objects are, either you're happy to lose them because you don't care, because the masses of the satellite are 10 to the 20 grams. So if you start out with 10 to the 22 grams, you can lose 99% of it and be happy at the end. So if you're happy losing some kilometer objects, you still want some meter size objects left over. And that's sort of the sweet spot for having stuff left over. If it's smaller than a meter, that's okay. And if it's 10 meters, that's also okay. But as it gets bigger and bigger, it's harder to keep the stuff in the system. So you have this binary collision, and it's probably small stuff. and we've done calculations to see how stuff becomes smaller and smaller. But I think those are the big parameters. We don't care too much what it's composed of because we just assume that it's ice, which has a density of 1. And so that's the mass of the stuff, the total mass of the stuff, what the biggest particles are, and the orbital parameters.
So somebody's asking if the Pluto Charon system must have. He's asking if the image was. I'm guessing it's the Hubble Space Telescope image. Must have been when Pluto and Charon were inside Neptune's orbit to capture that level of detail.
No, it actually didn't really matter. So for the Hubble Space Telescope image, where they were using the eclipses of one relative to the other, it didn't really matter because what happens is, just sort of imagine that you have a big circle of light and you put, a smaller dark circle across it. All you really need to do, and Pluto's pretty bright, it's 12th magnitude. So, and HST is a pretty big telescope for 12th magnitude. What you really need is good timing. So as Charon passes across the face of Pluto, and in the reverse, Pluto passes across the face of Charon, you're not really imaging so much as just measuring how much of light you see. And since you know how big Pluto is, if a certain amount of light goes away somewhere, you can paint Pluto and Charon with, pixels of different intensity and see if you can reproduce the light curve or the brightness of the eclipsing objects as a function of time. So I don't remember where the orbit was, but it doesn't make too much difference.
Thanks. Tony asked, what size time step was used in the simulations, or did that vary depending on whether it was symplectic or higher order?
The time steps. So we have the time steps in the symplectic are there are 40 steps per 6.5 hour period, orbital period of Pluto Charon, and we actually tested that. If you divide the orbit into 50 steps or 60 steps, that's also good. The more you subdivide that orbit, the better, but it takes longer. So 40 was more or less, 40 to 50 is about the minimum you can do and have a stable system. So if you do 20, you can divide Pluto Charon, orbit, which is 6.5 days, into 20 steps. Then the system is not as stable. And so you don't really trust your results as much. So those are the symplectic runs. When we do the higher order integrator, and so 6.5 hours divided by 40, 6.5 days divided by 40 gives you an idea of a time step for symplectic. When we do actual formation, when we're resolving collisions, we sometimes have time steps as short as 10 or 100 seconds because we want to resolve the collision and we want to know, because we want to know if particle A collided with particle B. Sometimes it's less than 100 seconds. So we've gotten down to a second sometimes because the collisions happen very quickly and you can miss. So what we do is we have a generic time step in these kinds of calculations, which is thousands of seconds, which depends on the density of stuff. If there's more stuff, the time steps are slower. And if we detect a possible collision, then we cut the time step by a factor of 2 or 10, depending on what we think is going on. And if that doesn't seem to work, another factor of 2 or 10, and we just keep cutting the time step until we can resolve the collision we want to resolve. And it may be that we have to do, the equivalent of, 1,000 or 10,000 seconds several times, or maybe even 10 times, before we get the right time step to resolve the collision. And it's not too clumsy. It's probably not as clumsy as the way I described it, Because sometimes we know, oh, we can go from 1,000 seconds right down to a second and we'll be fine. Sometimes we iterate a little bit.
It's kind of cool. Do we know if the various ices on Pluto's surface are stratified by composition or mixed?
So the thought is that I think they're pretty well mixed. I'm not, I'm not a geologist, so I don't know for sure. But my impression from what I've read is that the ices are pretty well mixed, but they're not all the same abundance of ices. So the dominant ice is nitrogen. And after that, there's water. And it's not too surprising it's nitrogen and water because those are very abundant things in the sun. So at least hydrogen, oxygen, and nitrogen. And things like methane and ammonia are somewhat abundant, but not as much as nitrogen. So even though ammonia is nitrogen and hydrogen, often the nitrogen doesn't find the hydrogen. Hydrogen finds the oxygen and then is stuck, and depending on what you have. So the nitrogen, I think, is the dominant one. And they're fairly well mixed, I think. And although the surface features are more complicated molecules that cause some of the colors. And I don't remember exactly which ones.
That's very cool. Any other questions, folks? Those are some good questions.
They were excellent questions.
Yeah. Bill is asking, are Pluto and Charon undifferentiated masses? Similar question.
So it's the belief, this is a complicated thing to figure out, but the models suggest that Pluto actually is differentiated, and what that means for people who aren't sure what that means, it's that Pluto has a core and a mantle, and the core is heavier or is denser than the mantle. It's not constant density throughout, and the core has more rock. And so the core is, has, if you could, take a square centimeter of the stuff out, and could analyze of the core and of the surface would be mostly ice, and the core stuff is more silicate rock. And it's believed that it's differentiated, and I think they have concluded that there's sort of an underground ocean. Charon has less chance to differentiate. It might not be big enough to differentiate, because what happens is they don't start out differentiated. They have, let's say it's a uniform composition bunch of rock and ice. What happens, it starts out frozen, but radioactive decays heat up the core, and the core can actually get pretty hot. It can get up to 1,000 degrees, and that melts everything, not surprisingly. And once things get melted, then you can, the heavier particles, the rock, fall to the center, and over time it will refreeze because the nuclear decays obviously have a half-life, and so they become less and less as time goes on. So it can refreeze. I'm not sure if it's refrozen, but that's what causes the differentiation. Is that initially it's all frozen, and the heat of formation early on isn't enough to differentiate it usually. But the radioactive decay does, and so Pluto is easily differentiable over 4.5 billion years, and Charon is harder to differentiate.
And I have a question on, do we have an idea of the cause and the age of the ice flows on Pluto?
So my understanding, again, I'm not a geologist,
Geology.
but I'll do my best here, because I have read about it, but I don't always remember it really well. What does happen on Pluto is that Pluto has a little bit of an atmosphere, and the atmosphere is caused by radiation from the sun and high energy particles from the sun that hit Pluto's surface, kick up the ices or even evaporate them as it were. And so the frozen nitrogen becomes sort of gaseous nitrogen, and it may go away, but because Pluto has gravity, it will sit there for a while. And I think one of the pictures is that the sublimation of the surface followed by refreezing, because the sublimation obviously is bigger when Pluto is inside the orbit of Neptune and closer to the sun than when it's farther away, because it's closer to the sun, so it's warmer, and it gets more photons. So there's more sublimation, and you can see the haze. And New Horizons actually took a picture, it's probably on the web somewhere, looking back towards the sun, where you can see the hazy atmosphere of Pluto. And as Pluto goes from, say, inside the orbit of Neptune to outside, that haze will refreeze. And how it refreezes can cause some of these, can cause stuff to condense again. And it can also cause it to flow, because it's getting heated in a differentiated way, because Pluto doesn't really orbit that fast. And it's always fixed. It's so, it does, have different, different parts of it do see the sun, but they get heated in a different way. So I think that's sort of right, but don't hold me, don't make my PhD dependent on that.
No, thanks, Scott. Appreciate that. All right, I think that's it for our questions. So, Scott, thank you so much for coming. We appreciate it. It was a very interesting talk. Got a lot of good questions out of it, too.
Well, thank you very much. I enjoyed giving the talk, and the questions were great. It was fun to discuss this with you, and enjoy the fall.
We will do that. Thanks so much for coming, Scott. Appreciate your talk very much.
Thank you for having me. I appreciate it.
All right, take care.
You too. Be safe.
We will all try that. All right, I'll give my final three. Thanks for everybody for coming. If you're interested in a virtual star party, we'll do that on Sunday night. It won't be long. I'm figuring 45 minutes or so for the star party on Sunday night. So that'll be at 7:30. We'll take a little tour of the planets at 7:30 on Sunday. So same bat time and on this channel, but on Sunday night. Thanks, everyone. Have a great evening.